Hello and welcome to this discussion about the F distribution. Before we move on to our final test of group means, which is the one-way ANOVA, I'm going to take a few minutes and explain something about the probability distribution that test is based on, so hence this video. So I'll be comparing it to the t-test and then discussing the problem that this F distribution solves, and then we'll be looking at the actual math behind the test itself and what that distribution looks like. So let's start off by looking at what we know. First of all, we know that the t-distribution can solve problems like x bar 1 minus x bar 2 divided by the standard error of the difference between them. We saw this with the independent samples t-test. This top piece is really a test of locations. Remember how we drew that graph and we said group 1 and group 2. We plotted out all of those points. Here's my x bar 1 and here's my x bar 2. And so really this top piece is showing me that I have a difference between the locations, in other words on this continuous scale. Between those two groups, between groups 1 and group 2. The standard error is what we're used to thinking about in terms of spread. In other words, standard error is how far spread out those different distributions are, and this is where we correct the degrees of freedom so that we can adjust that t-distribution so that it is adjusted away or towards the z distribution. One thing that you can think about is that this top part can be looking at a difference between the groups, and this bottom part, this spread, can be showing the difference within the groups. You'll be seeing this between and within a lot in the future. So within the group is how far each of the data points is spread out within that group, and then this top part, the location piece, is how far are the two groups spread out from each other. So if we were to draw where those come over here to the y-axis. In a way, you can think of this as signal to noise. In other words, there's just a certain amount that the data is going to be spread out just inherently. How much are those two groups really different from each other when you consider that there is kind of like this difference between them just inherently or within them? So once we have kind of looked at this whole idea with the t-distribution, the problem with a t-distribution is that we can only compare two groups at a time, and this top part can only accommodate x bar 1 and x bar 2. We can't really look at more than just two groups. And so let's say we have a third group and a fourth group and that kind of thing. One person might say, well, let's just compare group 1 to group 2, group 1 to group 3, group 1 to group 4, group 2 to group 3, group 2 to group 4, group 3 to group 4. And you can see that all of a sudden we're starting to have lots and lots of comparisons. And let me show you kind of in this little area right here why that's a problem. If we have only two groups, then all we have is 1 versus 2, group 1 versus group 2. And the type 1 error that we have because of that is, if you remember, is 0.05. Come over here to the right hand side. Remember how we talked about this decision. If we fail to reject the null and the null was true, perfect, we're set. If we reject the null and the null was false, also that's great. But if we do anything in these corners, then we're making an error. We're making the wrong decision. And this is the type 1 error. And usually when we talk about a 95% confidence interval, that means here we have 95% and here we have 5%, or 0.95 and 0.05. So here's our 0.05. Type 1 error that occurs. We have to set the cutoff someplace. The problem that happens is when we're comparing more than two groups, like let's say we want to compare three groups, we have to compare 1 versus 2, 1 versus 3, and 2 versus 3. Is this type 1 error now starts to become what's called inflated. So here we have the family-wise type 1 error actually goes up to 0.143. So 14.3% of the time, one of these we're gonna make a wrong decision just because of how many of them there are. Let's say we go up to 4 possible groups that we're comparing. That's what I've shown you here. We have 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4, and so we have 6 different possible combinations, 2, 3, 4, 5, 6, and our family-wise type error goes up to 0.265. In other words, more than a quarter of the time, one of these combinations, we're going to make the wrong choice about that. We're going to say that we reject the null, when really it was just by chance alone that we happened to draw that particular sample, or we measured whatever. As soon as we get up to 10 groups, there are 45 combinations. And at that point, 90% of the time, 90.1% of the time, we are going to make that type of an error. And so we don't want to be doing that. So this is the problem. When my daughter was little and I was explaining this concept to her in some fashion or another, she said, "Oh, Mom, I have the perfect analogy for that." We have a dog, and she goes out in the yard and does her thing. She makes a poo. And if there's only one poo in the yard, then the chances are, we walk across the yard, you're probably not going to step in a poo. But if she makes a poo and then she makes another poo and there's lots of poos out there, it's pretty hard to get across the yard without making that type of an error. And so the more chances you have of making that error, the more combinations of two groups, then that family-wise type 1 error just elevates and elevates and elevates. Hence, that is the whole reason that we have an F distribution, is that we need to be able to test all of these possible combinations instead of 2 at a time. We need to be able to test all of them in one test that has 0.5 error for the whole entire thing. And so what we do then is we take this T distribution, remember how we have the between and the within, and a magical thing happens when we take that same thing and we square it. When the T distribution is squared, it becomes F. And so then we have, instead of just the between and within on the top, we have the mean square of the between divided by the mean square of the within. See how we've squared it, squared it, squared it, squared it? And the nifty thing that happens is not only can we adjust the denominator for degrees of freedom, now all of a sudden we can adjust the numerator for degrees of freedom. And so, because of that, we are no longer limited to only 2 groups being compared to each other. Here, when we have the within, if we have n1 minus 1 plus n2 minus 1 dot dot dot, so however many groups, we are just going to have our degrees of freedom for that denominator, subtract those out. For the numerator, now we can have degrees of freedom for the numerator, and we're going to say degrees of freedom within, degrees of freedom between. This is what's called k minus 1, and k is equal to the number of groups. So now all of a sudden we have a distribution that can have degrees of freedom on the top and the bottom. And so I want to take a minute here and just draw how exactly that works. And so hopefully this will help you understand that a little bit. If we're thinking about a T distribution, which is similar to a Z distribution, it is bell-shaped and symmetrical, if I can draw it here. And when we think about the error that's happening, that's out here, far away from whatever we consider to be our test value, right? And so if we have a 95% confidence interval here in the middle, then 2.5% is in each of these tails. So if we have, let's say, degrees of freedom equal to 60, remember this cutoff, this critical value, is equal to -2 and +2. That t, the corresponding t, is equal to 2.000. So as the sample size gets smaller, more and more of that area falls into the tails. But just let's go with the degrees of freedom of 60. If we were to take this same exact curve and we squared the curve, what you would end up with now is no longer going to be bell-shaped and symmetrical. It ends up being a shape that is more like this. And if you square this 2 and -2, what you end up with is, if you have the degrees of freedom within equal to 60, then your F value is going to be equal to 4.000, because that's just squaring the 2.0. So let's say here's my F value of 4 along this continuum. Everything in the tail then after that would fall into the reject the null. Remember how if the t-value is over here in the tails, then we would reject the null on either the higher or the lower, as long as it's a two-tailed test. The F value is the same. If it's in the tail or more extreme than whatever is our cutoff value for that particular degrees of freedom, then this is your 5%, falls into the tail area. Then that's going to be the equivalent, and 95% is here in the under the curve in the area less than 4. So here's 0, here's 4. We have 1, 2, 3, 4. And this is if we have a degrees of freedom between is equal to 1. Now, as the degrees of freedom between changes, if it goes up and down, then the shape of this curve again keeps changing, just like our t-distribution here changes depending on the degrees of freedom. And there are now 2 dimensions that those degrees of freedom are changing, both in the numerator and in the denominator. And so this curve adjusts so that this cutoff value actually moves to the left or to the right, depending on both of these degrees of freedom. And just as kind of a reference point, the F value for degrees of freedom within is equal to 1,000 is equal to 3.85. So anything above about 3.85, here's df equals 1,000. df within. So anything, if you ever get an F value and your F value is like way big over here, then you can kind of just think about that as like having a t-value that's way far out. If you have an F value that's equal to 2 or 1 or 0.5, you can be pretty much for sure that that is going to fall into this fail to reject the null area over here on the left hand side. So that is a quick overview of the F distribution. I hope that is helpful as we move into the one-way ANOVA test.